Hello and welcome to the second in this short series of videos about noise. In this one we'll be looking at probability distributions in a bit more detail and how we can use them to calculate the expected levels of noise in a system. First, a quick quiz question. This is a probability distribution of a certain noise signal. It has a value of 0 for all values of the noise below -1 volt, a value of 0 for all values of noise above 1 volt, and a value of 0.5 for values of noise between -1 volt and +1 volt. So, what is the probability that the noise voltage at any particular time in the future will have a value of 0? And the answer is 0. There is no chance at all that the noise voltage at any specified point in the future will have a value of 0. Exactly 0 volts. If you understand why that is true, then you have understood what a probability distribution is actually telling you. The important thing to note is that P of x is not a probability. P of x times delta x is a probability. It's the probability that the random value x lies somewhere in the range between x and x plus delta x. But P of x is not a probability, it's called a probability density function. You have to multiply it by a small range of values, delta x, in order to get the probability that the random quantity is between x and x plus delta x. So, the probability that P of x is exactly 0, well, that would mean that the range x to x plus delta x would be 0. So delta x would be 0. So the probability density function, which is just a constant 0.5 around here, times 0 gives you 0. And the probability that the value x is 0 is therefore just 0. What we can do with the probability density function P of x is work out what the probability is of x being between any two given values. For example, what would be the probability that x was between 0 and a half? We do that just by adding up the probabilities that P of x is in any of the little ranges between 0 and a half. So, for example, consider this probability distribution, which has a value of 0.5 between the values of -1 and +1, and has a value of 0 everywhere else. Well, if we're interested in the probability that x is between 0 and 1/2, this point here, then what we've got to do is divide up this region between 0 and a half into a lot of small subregions, each of which has a width of delta x. Then the probability that x is in any one of these regions will be P of x times delta x. And all we have to do is add up the probability that x is in any one of these regions. Sum them for all values of x between 0 and a half. Well, as delta x becomes infinitesimally small, this just becomes the integral of P of x dx from 0 to a half. And since P of x is a constant in this example, it's just a half within this range, we can take that outside the integral sign, just write that as this, and that is equal to a quarter, or 0.25. Or, as we often specify probabilities in percentage terms, we could call it 25%. Now, you could also ask the question, what is the probability that x is somewhere between -1 and +1? Well, that is just the integral from -1 to +1 of P of x, which is a constant value of 0.5 in that range, and that is equal to 1. Now, note that there is absolutely no chance at all that the value of x is below -1, and absolutely no chance at all that the value of x is above +1. So the integral from -1 to 1 is actually equal to the integral from -infinity to infinity, since from -infinity to -1 everything is just 0, and from 1 to +infinity everything is just 0. That then says that the probability that x is somewhere between -infinity and infinity is 1. In other words, we can be 100% certain that x is somewhere between -infinity and +infinity, which is sort of obvious, really, when you put it like that, or at least I hope it is. But the important thing, and the reason why I did that, is to point out that this is an important formula and is generally true for every probability distribution. Integrated over the complete range of x, its random variable, in this case -infinity to +infinity, and the answer must always be 1. Because you're absolutely sure that at every point in the future, x is going to be somewhere between -infinity and +infinity. We don't know where, but we're absolutely sure it's going to be in that range somewhere. The two most common forms of probability distribution in electronic noise are the Gaussian distribution and the uniform distribution. One interesting thing about the Gaussian distribution is that the tails of the distribution, that's the extreme values up here and down here, in theory continue to plus and minus infinity. As the value of x increases to large values, there is still a finite, although vanishingly small, probability that the noise value x will have those very large or very small values. However, for the uniform distribution, that is not true, and the value of the noise x is limited to the range of the uniform distribution, in this case between -2 and +2. Gaussian distributions like this arise from some very common physical processes. You get a Gaussian distribution whenever you have a noise which is the sum of a large number of contributions of independent random variables. It's quite a good model for the random thermal oscillations of electrons and nuclei in a resistor or any type of conductor. That tends to give you these Gaussian distributions of noise. The different distributions are also reflected in time domain plots of the noise waveforms. This is noise with a Gaussian distribution. You'll see that this particular noise does get down to a value of -2 and almost up to +2. In theory, at least, if I let it run for an infinite amount of time, I would get occasional samples of the noise which were infinitely high or infinitely low, but they would be very, very rare. This is a uniform distribution. The noise is equally likely to have any value at all between -1 and +1, but never takes a value below -1 or above +1. These two noise signals actually have exactly the same RMS value, so they have the same noise power. But as you can see, the time domain plots do look quite distinctive. But how do they sound? Well, this is what Gaussian white noise sounds like. And this is what uniform white noise sounds like. Can you hear the difference? No, me neither. The ear just isn't designed to pick up the difference in the probability distributions of the noise. All it picks up is how much energy there is at all of the different frequencies inside that noise signal. And for white noise, as we'll see a little bit later, the same amount of power is in the same frequency bands of that signal. I'll talk quite a bit more about that in the next videos. Okay, that's all for this time. Next video, I will look more about the frequency content of noise and how we can distinguish different types of noise by their shapes in the frequency domain.